Kernel vector spaces. This is the very nice and interesting topic to see what are the vector spaces and what is the difference between the vector spaces and the set. Basically, we know that a set is the spatial collection of well-defined and distinct objects. But here, let's see about something more general, which is called the vector space. So, in a vector space, let's recall the definition of a vector space. So, this is the definition of a vector space. Please remember that this is very important, and these the properties of a vector space or its axioms must be on your fingertips to know the basic idea of a vector space. It's very interesting, but it's very much general. So for that, let V be any non-empty set we have in head. Suppose that you have any non-empty set. We know the set is a collection of a well-defined and distinct objects. And in that set, we have the two operations are allowed. One is the vector additions, like for the element of set, you can add the two elements with this plus sign. Plus sign is just like an operator. You can add two elements, and the other operation is the scalar multiplication with some constant alpha or some constant k. You are allowed to multiply k with some any vector or any element of this sector V, like k times u. This is called the scalar multiple of k u by k. And in general, this set capital V, which is a non-empty set, is called vector space over the vector addition with plus sign and scalar multiplication with k times u, like as you see that it's a ku. So we have a multiplication and the vector addition and scalar multiplication is allowed in that. So under that, V is called a vector space if it satisfies these important 10 axioms. The first thing is that if you take any two elements from this vector space V or this set V, then their sum is also in V. Like this is the very good property of a real number is that you know the whenever we add two real number, then their sum is also a real number. Then their sum is also belongs to the V. For instance, like if you take the element 10 and 20, the 10 plus 20 is also in the set of real numbers. But if you take any set like a finite set like 1 to 10 and pick the 5 and 10 from that, then 5 plus 10 is 15, which does not belong to the V. It means the closed set 5 and 10, 5 to 10 or 0 to 10 is not a vector space. So in this way, you can fail the properties and check that which all the 10 axiom will satisfy, then it will become the vector space. Another the good property of that one is that if you take any two elements of that, then it's also always satisfies this commutative law of addition. Like the sum of two vectors u plus v is always same as v plus u, and it also satisfies the associative law of addition, that u plus v plus w is same as u plus v plus w. And furthermore, in that set V, there is also a one nice property that there must be a zero element in V, which is called a zero vector, such that if you add 0 plus u is same as u plus 0 is equal to 0. So this means this property is hold for all elements of u in V. Like there must be a zero. Like if in a set you haven't a zero or identity element, whenever you add it doesn't becomes the same of that one, then this set will not be a vector space. So zero element must be the part of that vector space. And furthermore, there is also this is very important property of a vector space, that if you take any element of the set U, then there must be a minus U belongs to the V, such that this is also called a negative of U, such that U plus minus U is same as minus U plus U and equal to 0. Like additive inverse of each element must belongs to the V. Like if you have the set like which have some elements, then their minus of that one also will be that will belongs to the same set. Whenever you add the element, then the answer will becomes 0. And the another sixth property, which is also the very important. Why I'm say important? Because they have a different meanings, and this will tell you the idea of subspaces and other things. So if you take any scalar k and and if it multiply with the any vector of u, then k times u is also belongs to the v. Like if u belongs to the v, then k times u is also belongs to the v, whatever the k is. K is a negative number or positive number or any scalar or any real number. So look, we can assume that how much the set v bigger v is a vector. If v is a vector space, then how much it's a bigger, because if you it contains the positive entries, negative entries, zero is also belongs to that one. And furthermore, the seventh property says k times u plus v is same as ku plus kv, where k is a scalar and u and v are the vectors of a vector space v. The next thing is that k plus mu is same as k u plus mu. This is like a distributive law of a above one is a distributive law of a vector addition with scalar multiplication, and this is the distributive law of a scalar addition and vector multiplication. And moreover, the kmu is same as km times u. Like this is associative law. Under that, k and m's are vectors, and k and m's are scalars. Only u is the vector. And the last one is 1 times u is equal to the u. 1 is a real number. Look, you can see that this 1u is a very small one, like it's a very trivial one. But this 1u is equal to u is a very, very important, and many vector spaces, when many sets are not vector spaces, because of only this 10th axiom. Like we can see several examples where 1 to 9 are satisfied, but only the 10th is not satisfied. So that's why we can say that such a set is not a vector space. So these are the important criteria of a vector spaces. So first of all, we can check that in a set of real numbers. Set of real number is a vector space because if you take, you can see that sum of two real number is a real number. It also belongs to the same set V. If you take V is equal to R, V also satisfies this property. Zero also belongs to the V. And R vector space V, R if R is a vector space, you can check that each element have a additive inverse belongs to the R as well, capital R, like set of real numbers. Because if you take 10, then minus 10 is also belongs to the set of real number, like 10 minus 10 is same as minus 10 plus 10, that is equal to the 0. And if you take any real number and multiply with any scalar, then it also belongs to the set of real number. And you can also check that these properties are satisfied by set of real numbers. But on the other hand, we have a one trivial example, which is called the zero vector space. Zero vector space mean any set which contain only the zero. Like this is very small set, but non-empty set. The zero is the element of that one is. So if you take in a this zero can be subset of a R or subset of a R square. In R square, zero is the origin, like 0, comma 0. And in R cube, the zero is a 0, comma 0, comma 0. Like it's a triplet, contains the 3 points where all the threes are 0. And if we take these two operations, that if you take any of its element, obviously it's only have a 0. So 0 plus 0 is equal to the 0, and k times 0 equal to 0. And by default, if you check all these axioms, so these axioms are satisfied. The axioms of a vector space are satisfied, and hence we call it that this set, the zero set, is a vector space. Here you remember that every set is not a vector space. On the other side, every vector space is a set. Like because there are many sets which are not vector spaces. Like we can see the several examples of that one, because set is only the element of a well-defined and a collection of a well-defined and distinct object or distinct element. Now, if we say about Rn, then Rn is a vector space. Like how if you take the any two vectors of that one, n tuples mean n number of elements. You can take n equal to 1, then it's set of real number, n equal to 2, then it's a set of two tuples, up to so on. So whatever you take the n, then it's still a vector space under this law that if you add two vectors, then it will becomes u1 add with v1, also u2 add with v2, up to so on. It's again will gives you the n dimensional vector. and k times u is equal to the ku1, ku2 up to kun. So one can easily check that the all axioms from 1 to 10 of a vector space are easily satisfied by this vector space V. So if you have any question, then you can raise your hand, or you can also ask your question. Then later on, I will give you the answer of your question. Or you can ask your question, or just note your question, and you can ask your question at the end of this session. Okay. Now, the another thing is a vector space of a infinite sequences. Sequence is basically a function whose domain is set of natural number and it contains the infinite number. Then it means space of all functions is also a vector space. Like if you add two vectors, two sequences, then it will be add with in this way that the first element will be add in the first, second add with the second, third up to so on. And k times u is equal to ku1, ku2 up to kun. So we have addition and scalar multiplications are available. And one can check that these properties from 1 to the properties from 1 to 10 of that one is easily satisfied in a sequence, because you know that if you have a sequence like 1 2 3 up to so on, then on the other hand we have a -1 -2 -3 up to so on. Like if you add them, then the answer will become 0 0 0 0 vector will be also belongs to that one. And one time u is equal to the u again, the same vector we have. So the next example is the vector space of 2 cross 2 matrices. If we take a set of all all matrices of 2 cross 2 with real entries, all the entries are real. Under this operation, that if you add the two matrices u plus v, u is a 2 cross 2 metric and v is also the 2 cross 2 metric. And the addition in this way, the first entry will be added in the first one, second will be added in the second, third one will be added in the third one, and the fourth one will be added in the fourth. If you take this operation and apply u plus v in this way, moreover, the scalar multiplication with the u is k times the metric, where k is multiplied with each entry of a matrix. So one can easily check that this 2 cross 2 metric collection of all 2 cross 2 matrix is a vector space. It satisfies the all axioms from 1 to 10. And furthermore, if you take all the n cross n matrix or n cross m matrix, like 2 cross 3 matrix collection, the 2 cross collection of all 2 cross 3 matrix is also a vector space. All the 4 cross 5 matrices are vector space. Whatever you can take its dimension or its number of rows and number of columns, then their specific collection will always becomes a vector space under these laws, that the matrix addition and matrix with scalar multiplication. And so it satisfies, and you know the zero metric is also contained in 2 cross 2, where the zero element is that one. And for every vector u, if you take u is equal to u11, u12, u21, and u22, then minus u is equal to minus u11, minus u12, minus u21, and minus u22, such that if you add u with plus minus u, the answer will becomes zero metric. And moreover, minus u plus u is also equal to the zero. So it means one can see that one time u is also u. So here the all axioms are satisfied. So hence it will becomes a vector space. And in general, whatever we take the m or n cross class of a specific class, if you fix some number m and fix some number n, then the class or the set of all m cross n matrices is a vector space. It fulfill all these 10 axioms in similar way as the example of a 4 is satisfied above. Then there are some another classes of a, we have a several form of vector spaces. Like if we take the collection of all real functions, real valued functions, defined on the interval uh, from minus infinity to infinity, like set of real numbers, functions whose domain is set of real numbers. From that one, x is coming from minus infinity to infinity. Like f is a function, g is a function. We know that sum of two function is a function, and if you multiply k times with f is also will gives you another function, whatever the k is. if you put k equal to 1, 1 time f is equal to 1. So similarly, it fulfill all the certain properties of above functions. And you know, zero function is also a function. Whatever you put on that, the answer will be equal to zero, like a constant, or which sometimes we call a zero function or null function. So this also belongs to the class of real valued functions. And moreover, if f is a function, then we can also get a minus f is also another function. When you add f minus f, the answer is equal to the zero function. So, and one time f is f. So hence the space of all real valued functions where x is coming from minus infinity to infinity are satisfying all these properties from 1 to 10. It means that the space of all real valued functions is a vector space. Then let's see some examples. Like here, these are details are mentioned, and one can check that how they are satisfied. Uh, then we can go up towards some spaces which are not a vector spaces. For instance, like the set of all vectors of R2 such that you have this operation. If you take U is a vector from R2 where U1 and U2 are their the elements, two tuples, and V is equal to the V1, V2, and we define U plus V in this way, and K is any real number, and we have the scalar multiple operation is given as ku is equal to ku1 comma 0. This is the given one, and we just need to check that is R square a vector space under these two operations or not. If it fulfill any one of the property of that one, then it's not a vector space. One can check that if you take any two vectors, then add them, then the sum of two vector is a vector space, and it fulfill all the criteria of that one. Like even you can check that k times u is equal to suppose k is we have k is a 7 and u is a suppose any given number 2 comma 4. Then the scalar multiplication is available in only this way, that 7 times 2 comma 0, like the next entry it only fixed as a 0, so it will becomes 14 comma 0. Now what about the last axiom? If you know that 1 times u is equal to u, if you come, I'm asking about this axiom. As I told you that these 10 1 to 10 must be on our fingertip, so 1 time u equal to must be equal to u. Now if we have notice about that one, like u is 2 comma 4, and if we multiply 1 times 2 comma 4, the answer will be equal to only the 2, because the other 2 comma 0, because the multiplication is only allowed as k times u is equal to ku1 comma 0. The rest entry will become 0. Now it means u is, if 1 times u is equal to only the 2 comma 0, which is not equal to u, then it means the axiom number 10 is failed. On the other hand, you can check that all the 9 axioms are satisfied, but the axiom number 10 is doesn't hold for this set v equal to r square under these two operation, vector addition and under this way scalar multiplication. And you know that if any one of that axiom is not satisfied, then we conclude that v is not a vector space with that stated operation. Then there are also some other unusual vector spaces, like which are the vector spaces, but it's looking something indifferent. For example, if we have a v is a set of all positive real numbers, and we define the operation that u plus v equal to u times v, and k is any scalar, k times u is equal to u power k, and one can check that it will fulfill all the axioms, all the criteria of that one. For instance, like if we can check that u plus 1 is equal to u times 1 equal to u, and also the for every element the 0 is also available, or for that one is such that it will be hold these conditions. And if u is a vector, then minus u will be equal to 1 by u. Like you can see that u plus v is equal to u times 1 over u, and actually 1 is equal to the one is the zero operator, like zero vector is equal to 1 for that one is because if you take u plus 1 is equal to u times 1, which is equal to again u. So it means 1 doesn't affect anything on that one. So 1 is the zero operator of that or zero vector of this vector space. So one can see that all these axioms are satisfied, and hence this the set of all positive real number under that operation is a vector space. And then if we comes towards some conclusions of that one, since the vector space we have the 10 properties which always be satisfy. So under that 10 properties, we have this thing that if we take any scalar 0, 0 times u is equal to the 0. Remember that u is a vector because every vector will be shown as a bold sign. And this 0 is a vector because zero, the bold 0 and u are vector, and but the simple 0 is a real number or the constant, or so you can say it's a scalar. Scalars are always real number, whatever that one is. Similarly, k times 0 vector is always equal to the 0 vector, and moreover, the minus 1 times u is equal to minus u. Like the k times u is equal to ku. So and also the other properties. So one can see that it will always give us this thing. And moreover, if we have a k times u is equal to 0, then either the constant k equal to 0 or u is equal to 0. So these are the properties that are uh, by default hold in a vector space V, because if V is a vector space, then it must have these 10, it always fulfill these 10 axioms. Okay, so now if we see some problems from the textbook, let's see some of that one as it's available over here. Like determine which of the following set is a vector space, and if let or also check that which one it doesn't be satisfy. For instance, if U is a set, uh, it contains the element of a R square where x comma 0 with standard operation of R square. Standard operation of R square, mean if you add two vectors, how to add two vectors, and alpha time k times u is equal to the k times u1 with comma k times u2, these axioms. So need to identify that which of the following set is a vector space and which of the following set is not a vector space. Um, Similarly, if we take V, a set of x, y equal to r square, where y is positive. We need to check that is this vector space or not. If some property doesn't be hold, then we need to specify that one. For instance, like if you put 1 times u is equal to u, like if you take u element of that one, where x comma y, remember that y always be a positive. What happened if we multiply with some negative constant and then check that it fulfill the property where y is a positive of that one. For example, if you multiply the minus 1 with the element of a capital V, will again the element still belongs to the V or not? Because we know that if any vector u belongs to the vector space V, then k times V is also belongs to the V for all values of a k, where k is a scalar. And if you multiply with a negative element, you can see that minus negative numbers will be changed the sign of a y, because if y is greater than equal to 0, uh, then like if you are taking the 2 comma 3, then what about the minus 2 comma 3? Is minus 2 comma minus 3 also belongs to that one? Like if you multiply the minus 1 with that one, this one. So similarly, we need to check these properties and see that which of the following is a vector space or and which of the following is not a vector space under the given conditions. Similarly, in the problem number 6, we have a vectors of R3. R3 mean three-dimensional vectors. U is a U1, U2, U3. V is a V1, V2, V3. And the thing is, the scalar, the vector addition is available as u plus v is equal to u1 v1, u2 v2, u3 v3, and k times u1, k times u is available as a ku1, ku2, comma 0. The last element is equal to the 0. Now the thing is, compute the following, that u plus v and ku, where u and v are available, are on some specific vectors and k is a some specific constant, and then determine whether the axiom 7, 8, 9, and 10 hold or not. This also gives you the idea of it, a given example, given problem, as we saw that over here we saw some example where V is not a vector space. For instance, the following example will be helpful to you, that if we have this operation, the zero of that one is. Here you can see that this is the R square under these two operation is satisfies the all axioms from all the first nine axioms they are satisfying, but the last axiom is failed. The axiom number 10 is failed, where 1 times u is equal to the u. Similarly, here you can see and check that is the same axiom number 10 hold or not, like 1 times u is equal to u or not, where u is suppose 1 2 3 or 1 1 1. If you take u is a vector 1 1 1, then is 1 times u is same as 1 1 1 or not. If it doesn't hold the axiom number 10, then you just tell that the 7 8 9s are hold, but the axiom number 10 doesn't satisfy. And this is the one result which is taken from the last property of a the last property of a vector space, as you know that if ku equal to 0, then either k is 0 or u equal to the 0. So similar, we know that vector space has always satisfies the first 10 axioms. From that, one can conclude or one can show that if we take ku equal to the 0, where k is a constant, u is a vector, and this 0 is a vector. Because if something is bold, then it means it's a vector. And if something is not bold, then it means it's a constant. This is the constant 0 or real number 0. Then either need to show that k is equal to 0 or u equal to the 0. And the next is another important thing, which is we have the two numbers minus infinity and infinity, and r is a set of real number. If we add these two numbers, minus infinity and plus infinity in r, then it will becomes a bigger set. And r is a set of real number, and set of real number r is also a set. R is a vector space, but if we add the infinities, then it's make a something problem. What the problem is that, here the operations are available. K times infinity is available over here, where k is either positive or negative, or k is equal to the 0. Then we have these conclusions around along with these operations, it's a scalar multiplication and the additions, the infinity additions and minus infinity additions, these are available. The relations are available over here. Then show that this extended set of real numbers, where infinity and minus infinities are included in that, is not a vector space over R, because the scalars are coming from the R. So one can see that these properties doesn't be hold. There are some conclusion that we know that infinity plus infinity is infinity. And also, if you take minus infinity plus minus infinity is the again minus infinity. But another on the other hand, infinity plus minus infinity equal to the 0. And you can use these relations and see that it's violate the axioms of a vector space from v1 to v10. If you just show any one of the axiom which doesn't hold, then you can conclude that it's not a vector space. Because if we want to show that if any one of the given set is not a vector space, then at least one axiom is okay to show that it's not a vector space. And if you need to show that it's a vector space, then you must satisfy all the axioms, that it satisfies all 10 axioms. But if you need to show that if you are going to show that it's not a vector space, then only highlight and only show those axiom with which that axiom which it's the given set doesn't satisfy. So these are some questions related to that. And furthermore, we have some of the notes on that one. So here I will also upload something about that one regarding the general vector spaces, which are beneficial for you, and you can go through from that. So, but if you have any question, you can ask your question now. Students, yes, please.
Yes, Professor, could you please go over the example that you showed there on page 174 that I just didn't understand, whereby there's 7 times u and then it's not part of the vector space 174. Yes, for
Yes, one, this
example.
one. Okay. Well, let me
Yes, where it
find.
shows that it's not part of the vector space. Like I just didn't
Okay,
get it.
okay. Okay, fine. So remember that we have this operation is available that k times u. Let me make a u as a bold to see that. Uh, can you see the screen now?
Yes, Professor.
Okay. Well, so k is any scalar, and it's we just call it's u1 comma 0. This is the given operation, and this is hold for all the u. This we call it the vector u. And we know that the entries of u1 is like u is a u1 comma u2, and that belongs to the r square. Okay, as you know that this is the given operation we have. Uh, just recall it that this operation we have k times u is same as k u1 comma 0. Uh, this is the given operation. Am I right? Can you hear
Yes,
me?
Professor. Yes,
Okay.
Professor.
And we need to show that the 1 times like 1 times u is equal to the u. Am I right? Because you know the what is the axiom number 10? The axiom number 10 is always 1 times u is equal to u. Okay? Now, if we need to show that this one, if this does not hold, then it means it's not a vector space. Like it must be hold for all values of a set of real numbers. Like if you take u any vector, u is equal to say, uh, let us take, wait a second. This is a vector u. Suppose I am just taking as a 2 comma 3. Any vector, if we take u is equal to this one, then what about the 1 times u? 1 times u will becomes 1 multiply with the 2 comma 0 according to the given scalar multiplication. And then you have noticed that then it will becomes 2 comma 0. Then tell me, is this equal to again u or not? The u is 2 comma 3, but the here answer is 2 comma 0. Is this equal to u or not?
Not equal to you.
Not equal to u. Well, it means it does not equal to the u. So, but we know that if the given set R under these two operations is a vector space, then it must fulfill this criteria that u plus I think what happened. Uh, wait a second. Yes. So it always fulfills this criteria that 1 times u is equal to u as the given condition. But here we have noticed that we get some specific vector in R square for which it does not hold. This is the vector in R square, okay, for which the given condition does not hold. It means 1 times u is not equal to u. Hence we can say that uh, the axiom does not hold. Understand the idea? So here, if you can see that, for instance, the same thing, like u1, u2, but you know that is equal to that one, and if you take specific value like 2 comma 4, if you put 2 comma 4 over here, then 1 comma 2 comma 4 is only the 2 comma 0, which is not equal to 2 comma 4. So it means the axiom number 10 is failed to hold for certain vectors. And similarly, for this one, you can easily check that the axiom number 10 does not hold for this set V, where V is a vectors of a three triplet, like from coming from R3. So the axiom number 7, 8, 9 will be hold, but axiom number 10 is not hold. You can also give some specific example in this way, like you can take some vector 2 comma 4 or whatever, then you can 2 4 6. If you put 2 4 6, then 1 times 2 4 6 will becomes the 2 4 0. And we know that 240 is not equal to 246. It means 1 time u is not equal to u. Hence, the axiom number 10 does not hold. I hope your question is clear now.
Yes, thank you very much, Professor.
Okay, fine.
Sir, can you please repeat what you just said on problem 6?
Okay. Uh, well, in problem number 6, I'm saying that look, in the first part, you need to compute u plus v, where the operation is available, how to add the two vectors, and also k times u, need to compute ku, where k is available, u is available, and the formula is available. Like use only this formula and to compute ku. And the next thing is determine axiom 7, 8, 9, and 10. You know, where are the axiom number 7, 8, 9, 10? Here we have the 7, 8, 9, and 10. If you will, just I'm telling you the hint that if you compute 7, then hopefully it will hold. Axiom number 8 will be hold for this problem number 6. Axiom number 9 will be hold for that. But what about the problem number 10? As initially I told you, the last property makes sometimes a problem for us. It always be satisfied that 1 times u is equal to u. Here, suppose your u is a vector like 1, 2, 3. Suppose I am someone taking u is equal to 1, 2, 3. Then tell me 1 times u will becomes what under this operation. If u is equal to 1, 2, 3, then 1 times u is equal to, can someone tell me? Just tell your answer, whatever your answer is, maybe correct or incorrect. So I'm again telling that u is equal to 1, 2, 3. And then what about the 1 times u? If u is equal to 1, 2, 3, then u is equal to?
Hello.
Yes, please.
I think you will be. You said you. Can you hear me?
Yes, yes, yes.
Yes.
Appreciate. Yes,
Well,
please. Go ahead.
you said you said that you must prove the axiom 10, right?
Yes.
And then you
We need
and
to
then you
check
said
that axiom number 10 hold or not.
Yes.
My claim is
So
axiom number 10 does not hold according to the light of the previous example as I have shown you.
yes. So with this axiom 10, I just want to ask something. That one, does it multiply the first element only?
No, look, the the operation is available here. K times u is equal to ku1, ku2, and equal to the 0. Last element will become 0. That's it. This is the rule. This is the formula. And we need to check that is one time u equal to u or not. And I'm saying that if I take here u is equal to 1, 1, or suppose u is equal to 1, 2, and 3. U is equal to the first element is 1, second element is 2, and third element is 3. Like here, let me write for you is that I have a one vector u.
Professor,
Yes,
sorry
please.
to
Its
interrupt.
entries are suppose 1, 2, 3. Then, and you know the rule is k times u is always equal to is equal to k times u1, k comma k times u2, and the last element is equal to the 0. So this is the formula, this is the rule. Then can someone tell me what about the k times 1 times u will be equal in this
Professor,
case?
It'll be
One.
it'll be equal to 120.
It will be equal to 1, 2, and 0, because we are taking k is any scalar. If we take k equal to 1, that is equal to this. And will it be equal to again the u or not?
Not equal to you.
axiom number 10 will not
Not
hold.
equal to 0. Yes. Goodbye, because u is fixed 1, 2, 3. And under that formula, it will be equal to 1 u is equal to 1, 2, 0, which is not equal to 0. So it means the axiom number 10 is failed in that case. So hence axiom number 10 does not hold. So this means that the given set are three, like all three orders of a three triplet. So this is a it satisfies the axioms, but it's not a vector space because the last axiom, one time u is equal to u, does not hold. Hence, we conclude that this V is not a vector space under these two operations. One is vector addition and other is scalar multiplication, vector with scalar multiplication. Do you have any other question?
Okay, so for
Yes,
problem
perfect. Yes, the answer is correct. Like if you put k equal to 1, then ku is equal to 1 to 0, which is not equal to u. Perfect.
so say we create values of our own, ne? Is it fine?
Yes, like look, two things. This is the claim that u is coming from the all vectors of R3, whatever the vector is. But if you want to disprove something, you can take some counter example or some counter vector, like I have one vector for which given thing does not hold, then that is sufficient. Okay. Similarly, suppose there is a question in exam or some question in where like you have a sum set and you have a two operations are allowed for all elements of that. One is that u plus v is just adding in this way. The two vectors you need to add in this way, and k times u you can just take in this way. Then the question is this vector space or not? Then what you need to do? If you are you have a good practice and you only mention that here I have one example only, that if I take u is equal to this, some counter example, some counter vector, maybe you take u111 or 1 comma minus 1 or any vector, any example, and you show that this law does not hold, hence you conclude that it's not a vector space, then you will get the full marks, because you concretely tell that this is the problem, this is the reason for that's why this is not a vector space. So it means if you want to disprove or show that this thing does not hold, then only need to show that axiom. And furthermore, there are some in the next lessons we will see further about vector spaces where the more condition does not hold. if you specify any one of that and show that on the base of that it's not a vector space, then it's sufficient. Like suppose my this set, like if I go towards the problem number 2, the set of x, y, x belongs to the R square where y is greater than or equal to 0. Just I tell you it's not a vector space. Maybe it satisfies 7 properties, but only 3 does not hold. But if someone tell that, look, the condition number suppose 8 does not hold, and that's why it's not a vector space, and he prove, then it means he fulfill for the criteria for a full marks. And instead of showing the all axioms and need to show that, look, this axiom is fail. So I'm just telling you that if you want to disprove or need to show, then any counter example will be sufficient. As here we are taking the counter example and we are claiming that, look, it doesn't hold for some specific numbers. And beside, if you want to show that it's a vector space, then you need to show the all axioms. For example, this set u x comma 0 with standard operations. Standard operations, you know that what are the standard operations, and you need to show that is this vector space or not. Like it's a vector space, u is a vector space, and you need to show the all properties, like determine whether they are vector space or not. So it means you need to show that it's a vector space and it fulfill the criteria of a vector spaces. And here, for those which are not vector spaces, you need to specify that, look, the following, due to the following conditions, if the following condition does not hold or following axiom is not fulfilled, that's why it's not a vector space. Any other question, please?
Hi, Prof. Sorry, just with with problem 8, with
Okay.
with those infinities. So do you use those bottom, that k plus infinity equals infinity plus k equals infinity? Do you use that to disprove the axioms, or what do you use?
Look, yes. So this is the part of a question. Like like if we say that, what about the u plus v? Similarly here, or also the what times ku. So here k is any real number, and k plus infinity is same as infinity plus k is equal to infinity. So these are the properties of a this set R, which have the following things are hold. And the interesting thing is that, uh, look, under that relations, this set is not a vector space. Although R is a vector space, but if you add these two infinities, then it's violates the definition of a vector space, and you need to figure out, maybe there are 3 conditions or 4 conditions of a vector space which does not hold. But if you specify any one of that, like look, and you need to show that, look, the following one is does not satisfy. For instance, here we have the 10. Suppose you are to show that number 9 is doesn't hold, or 8 is doesn't hold, any one if you show and prove that, look, it doesn't satisfy because of these how many relations, 1 2 3 4 5 6 7. So these are the 7 of that one. So if you show that any one of that one will doesn't hold, then it's mean you done. And it's proof that the given set R union with these two infinities is not a vector space. Again, I'm telling you that here, any one of you need to show that at least one of the axiom is failed. Here, it's quite possible that the maybe 3 or 4 uh, are not satisfied. But if you shown any one of that and show that, look, according to that one is doesn't hold, so that's why this is not a vector space. You can see that infinity plus minus infinity equal to 0, how it will react and how it fail the given one from that one is. Definitely at the end, I will show you the solutions of all problems, but this is for your practice to see the concept and see that how this, like in this problem specifically, you can see that how infinities makes a problem. And another set thing, this is extended, extended set of extended uh, collection of the elements, which is even not a set. You know, the set is a well-defined and distinct objects or distinct elements. But infinity plus 1 is again infinity. Like if you put 1 plus infinity is infinity, 2 plus infinity is again infinity. So this also violates the criteria. Like here you can check the thing is how it fulfill how it's make a problem. What about if k is equal to the 0? Like 0 plus infinity is infinity. Look, if you put k equal to 0, 0 plus infinity is equal to infinity, and 1 plus infinity is equal to infinity. Does it means the 1 equal to 0? So like this kind of things you can see and you can conclude that this makes a problem and hence it's not a vector space. So I'm asking about the property number 4, which also violate because there is not a constant 0 will be hold for that. So, but if you will see this kind of things on the problem number 8, then you will see that there are certain properties or certain axioms from here which doesn't fulfill from that extended collection. So hence this collection is not a
Yes,
vector space over the R.
Professor.
Yes, please.
Yes, if I can just confirm if I'm hearing you clearly, you are saying that if the set is not a vector space, I only need to prove one axiom that it does not hold, then it is not a vector space. Whether there are 3 or 4 axioms that does not hold, as long as I can prove one, it is sufficient.
Exactly, it is sufficient. Yes.
All right. And
Yes.
if I am saying the set is a vector space, then I need to show that all 10 of them.
All. Exactly. Need to show all. You are bounded to show all of that. That's why it's a vector space.
All
Like
right. Okay.
so look, this is the you know, like this is the if you are like suppose you are a teacher and you want to take the exam of someone and you need to show that some guy is fail, then at least you show that at least one subject you show that he is fail in maybe in his O level or A level or any subject is fail, it means he is fail in full of that. And so the counter example will be sufficient. You can say that maybe he's fail in English or something. But on the other hand, if you need to show that he is passed, then it means you need to show that all the 5 axioms or all the 5 he fulfill the criteria or he is passed in all of that.
Okay.
So
Thank you, Prof. It's
yes,
clear. Thank you.
perfect. And for not showing, you also can go through with some with some counter example or counter vector. Like as I'm saying that, look, in R cube you have too many vectors, but you can choose any vector from that for which you need to show that for that if I took this vector then it doesn't hold. Beside, if someone says that, oh, I am taking u is equal to like like you just need to make a counter like, but for some vector it is hold. For example, if I take 0 or maybe here I take 1 2 and 0. Look, tell me, if I take u is equal to this one, then what about 1 times u is, then in this case 1 times u equal to u. Understand? If I pick u is equal to 1 to 0, then 1 times u is equal to u. It means for that vector it hold. But if I take u is equal to this one, then it doesn't hold. So for a counter example, you need to specify and you need to trace those collection from the given set for which it does not satisfy. Understand my point?
Yes, Prof. Yes.
Also, if someone take here 000, like u is equal to 000, then it always get 1 time u is equal to u. But you need to be check maybe 111, then for 111 1 time u is not equal to u. Okay, I hope you understand the idea of that one. So best wishes, and if you have any specific question you can ask maybe right now, or also you can ask in the group. Okay. if there is no any further question, then we can close the session now, and best wishes.
Thank you, Prof. Thank you.
Okay, best wishes and goodbye. Bye.